Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. Today we're going to get to gases. So this is going to be a real quick opening, a little review. I'm not going to do a whole lot of practice on the review problems because we've sort of done them before. I just want to do that. We're then going to take the two concepts that deal with varying process that are slightly different and do those. All right, so gases. The gases, defined gases, is equal to the amount of force in newtons divided by area in meters squared. A pressure then is F over A, where it's newtons per meter squared. A newton per meter squared is a Pascal. Now, you'll be used to working in pressure in kilopascals. We'll just simply have to divide that by 1,000 pascals in a Pascal. 1,000 pascals in a kilopascal. All right. Now, let's do a problem here. Now, I'll explain what's going on. As you experience pressure because of the atmosphere above it. And the reason why we get less pressure the higher we go is there's less atmosphere pushing down on us. So we're going to do some problems dealing with how that pressure applies to specific areas. Okay, let's take a look. Calculate the pressure upon a floor tile 50.0 centimeters on a side. If the mass above the tile that's the air pressure, has a total mass of 1,984.334 kilograms. All right, so we go to our equation. P is equal to F over A. And F is going to be M times A. That's from physics. Mass times acceleration is force. Now, what's the acceleration here? Mass acceleration here is the force due to gravity. And that value is 9.8 meters per second squared. So take the mass given there, 1984.334 kilograms. A kilogram meter per second squared is a newton. So we have 1,900. Real quick, the reason why it's not 2 sig figs is this is a constant. 446.47 newtons. Now we take... Sorry, that's 19,446.47 newtons. Area is length times width, but since it's a square, that's just me length squared, so 0.500 meters squared is going to be 0.250 3 sig figs meters squared. So if we take 19,446.47 newtons divided by 0.250 meters squared, a newton per meter squared is a Pascal. Sig figs, we only have 3. So we're going to get 77,800 pascals. Divide that by 1,000, so we're going to move it 3 places to the left, and we end up with 77.8 kilopascals. That's my answer. Let's try one more of these going the opposite way. So let's try determine the mass over a tile. Now, this is going to be more practical. How much mass is in the atmosphere if the pressure is 721.5 kilopascals over a tile that's 0.25 on a side. So a 0.25 of a meter on a side is the size of our tile. All right. First thing we do is take our pressure. We've got to deal in pascals, not kilopascals. So we're going to move it 3 places to the left, to the right, and end up with 721,500 pascals. Now remember we said that P is equal to F over A. We're trying to find the mass. That means we have to find the force first. So F is going to be equal to P times A. What's on the bottom comes up. P is across. It's still the same. So it was division. It's going to be multiplication. F is equal to P times A. So we take our 721,500 pascals times area. It's 0.25 now, and it's a square, remember. It's going to be 0.25 squared. 0.25 meters squared is going to be 0.063 meters squared. Now we said a Pascal is a newton per meter squared, so the meter squares cross out. We end up with 45,000 because we can only have 2 sig figs. Only 2 sig figs of 0.063. Now we said, again, that F is equal to M times G. We're going to solve for mass. Mass can be F divided by G. So we take our 45,000 newtons. Newtons is a kilogram meter per second squared. Divide by our 9.8 meter per second squared. Newton meters per second squared cross out. We end up with kilograms, 46,000 kilograms. And that seems like an awful lot. And it is, except your body's just used to it. And that's what we experience. So this, we don't feel it because we're pushing up inside of the body, the same pressure is pushing down. All right, now what we're gonna do is just run through the rest of the laws that we've covered before. We're not gonna do any examples here because we've done those before. If you're not sure, look back in the Chem 1, the practice we already have there, okay? So, gas laws we talked about, Boyle's law, relationship between volume and pressure is the inverse proportion. So as pressure goes up, volume goes down. If temperature is constant, Charles' law, volume and temperature look at proportion. Volume goes up, temperature goes up. If pressure is constant, and Gay-Lussac's law, pressure and temperature look at proportion. So pressure goes up, volume goes up. Pressure goes up, temperature goes up, volume's constant. So we put those together, we get the combined gas law, which we talked about, 4P1V1 over T1, P2V2 over T2. And we've talked about those before. We'll use those in some of the equations we'll work with later. Now, there's another gas law we didn't talk about last year. And that's Avogadro's law. It says the relationship between the moles and volume is directly proportional. So as the number of moles go up, the volume will go if both temperature and pressure are constant. Now, why am I introducing that? This is actually what we need to include ideal gas law. That's where the N comes in the ideal gas law. So if we put P1V1 over N1T1 is P1V, that's how we get those values. And our constants, of course, are 0.0821 liters atmosphere per mole Kelvin, 8.31 liter kilopascals per mole Kelvin. If you don't have either of those values, that's where we go from there. And we're going to stop there. We're going to do Graham's law and Dalton's law as separate processes, and we're going to add some things to them. So make it advanced chemistry, chemistry 2. All right, that's it for today. Take care. God bless. Bye.